Hello everybody and welcome to the Carl and Cymru revision sessions. The session this evening will focus on topic on well, as you can see, the P block and D block, which I think is topic 1.3. Sorry, yeah, 3.3. Get my units wrong. It will be presented by Miss Stevens from the school Bropeda. The session will last around 45 minutes, where Miss Stevens will run through the relevant content. If you have any questions during the session, please use the question and answer section and we'll do our best to answer you. You will see there's a hyperlink in the Q&A section. If you happen to leave your name and email address, we would love to keep in touch with you so we can send you information about future events. You can click on the link at any time during the session. Today's session will be recorded and the recording and any relevant resources will be uploaded to the e-sgol website under the Carl and Cymru tab. So thank you, Ms. Stevens, and over to you.
Good evening to you all. As you can see, the first slide there, I've just pulled up quickly for you, is the advanced information. I hope you've all already been informed about this advanced information. So it's released by the exam board, was done a few good weeks ago now, really. But the intention of the advanced information is really to give you a bit more focus in where you need to target your specific revision as you lead up to these crucial weeks ahead. So the following areas of content are therefore suggested to focus on, and as you can see, one of the top lists there is the P and the D block, which is why I'll be focusing on them this evening. I won't be doing the content in superb detail, but I will be doing the content itself at quite a rapid pace. And that's not because I'm spiteful, it's because there are actually two previous sessions that I'd like you to focus on if you want more in-depth information, which was done by myself back in 2022 spring. So if you would need a bit more in-depth understanding, then obviously go back and look at them, those sessions specifically. I'd also say if I am going at a hefty pace, there is that pause option, of course, open to you. So I would say just take a break, pause, process what I've just said, and then move on. That is always an option to you, of course. Okay. So just to be careful as well, do not lose focus on the fact that there's very much a synoptic element in both Unit 3 and Unit 4, and of course Unit 5 as well. So anything in Unit 1 and 2 can be further developed in A2. And on top of that, please keep focus on the calculations from Unit 1, which can be assessed at any point, really, including Unit 2, which maybe some of my own pupils don't always take notice of. Okay, so the specifications you can see there is quite in-depth for the P block, and I'm going to focus, however, on certain strands more than others this evening. So that is familiar to you. I'm sure your teachers or you independently have got a copy of that and you've got it sorted, so that shouldn't be anything new to you. But what I'm going to do is just recap for you some of the content from the previous session and just the trends that you're meant to be familiar with. So, for example, the trend in electronegativity, down and across, of course, so considering the periods as well as the group trends, but also that the atomic radius obviously decreases as you go across, but as you go down, obviously increases. So just do not lose focus of the just general trends that you do have in your head, I'm sure, and just try applying it as often and as frequently as you can to any sort of questions that you come across. So what are the main themes that I'm going to be focusing on this evening? Well, as I said, I'm doing the P block and the D block. So I'm going to do the P block initially for you. And from the P block, I'm just going to recap on certain strands like the inert pair effects and how that is often and commonly examined. Electron deficiency and how that can lead to quite an interesting side of its chemistry. The expansion of the octet rule and how that can lead to different shapes of molecules based on the VS-CPR. And the isoelectronic behaviour of certain P block substances like the graphite diamond versus that boron nitride that we'll be looking at. Okay, so oxidation states, you should be a bit more confident now you're in year 13 and A2 that you can allocate oxidation states quite confidently, I hope. But what you will have developed during this year in the Unit 3, of course, is the fact that there is this interesting trend as you descend the P block where it exhibits this science perfectly. So when you've got group 4, you have that expected oxidation state of +4 at the top, which is carbon. And that's why you've got things like carbon monoxide being such a good reducing agent, of course. But as you descend, you see an interesting flip in that trend where it will tend to drop by 2. So you've got group 4 that changes its preference from 2 to 4, and vice versa. Either side, you've got that flip side of going from 3 to 1 and from 5 to 3 as well, which we'll look at. But why? Well, look, let's revisit initially why group 4 tends to bond 4 times. Okay, now that is something you've picked up on in organic chemistry in year 11 even, but maybe possibly didn't question in too much depth. Well, it's important to know that when bonding occurs, you are familiar with pairing in that kind of covalent classic GCSE bonding, pairing electrons with another electron covalently so that they all are happy and they achieve the octet rule. But let's be clear, it is important you also understand that when they do pair that electron, that they have to be in opposite spin to each other, because otherwise they would repel each other. Okay, so what you have is that you'll promote that electron from the 2s, in the case of carbon, up to the 2p. Okay, and that then opens up this availability of 4 unpaired electrons, and that therefore leads to a preference to bond 4 times. So you've got this excited state of 1s to 2s1 and 2p3, etc. in the carbon elemental form. So it hybridizes into 4 orbitals of the same energy. Okay, so hopefully that is something that's familiar to you. If not, please go back to that P block session that was an entire 45 minutes from spring 2022. Okay, so what happens down the group? As I said, you do have the occurrence of both the +2 and the +4 for carbon, hence carbon monoxide, but you should be aware that the least stable oxidation state of those two is +2. For carbon, that's why carbon monoxide is such a good reducing agent. Travel all the way down to that bottom of the group there, lead, and that now has a preferred oxidation state of +2, of course, and its +4 is therefore an unpreferred one, and it leads to it being a good oxidizing agent in certain reactions. Okay, so the low oxidation state then have a greater percentage of ionic bonding as well. So in group 4 specifically, you've got the +4 that's +2 that's mainly ionic, whilst the +4 is mainly a covalent nature to that compound. Okay, so down the groups, why does this happen? Well, you've got the obviously the atoms getting much larger as the atomic radius is increasing on descent. As a consequence of that, you've got the bond lengths that are getting longer and weaker. The bond pair becomes further from the nuclei, which is what obviously is keeping that electrons attracted to the nucleus. The bonding energies as a result reduce, and there's insufficient energy returned then to the system to balance the energy required to promote the electron from the s orbital. Okay, and because you don't get payback in a sense in this promotion, it doesn't occur, and that s pair remains inert or does not get involved in that reaction. Okay, so it's called the inert pair effect, which hopefully you're well familiar with and comfortable with by now. In the same sense, you've got group 3. Well, as no shock, therefore, you've got the s electron promoted again to the p orbital. Okay, as you go down, this becomes less favourable, and the payback isn't sufficient, so there's insufficient energy returned. So you get the appearance then of, in group 3, this indium and thallium preferring to show or exhibiting a +1 oxidation state, of course. Okay, 5 go one side, the other side then to group 4. Then obviously you've got this again shifting of this by a figure of 2, and it's all relating all the time back to this, whether it is energetically favourable to promote the s electron or is it not energetically favourable. So the same trend as you go down, it does not get sufficient payback, and therefore you see the occurrence of a +3. It's only really evident in bismuth, I should emphasize, in group 5, but nonetheless it is again related back to that very same thing, which is the inert pair effect. Okay, right, so electronic structures. This is the second thing I want to focus on, because this brings into play this element of electron deficiency, and it's leading to what is often known as kind of coordinate bonding, of course. Okay, so what you have there is you've got aluminium. So if you notice in aluminium, it's got its own valent electrons there, but because it's only got 3 electrons, it can only really bond 3 times. So as a consequence, when it does bond with chlorine, chlorine will only offer it 1 electron initially in that sense. So you'll notice there that you've got an electron deficient central atom there for the aluminium. It's only got 6 electrons in its outer shell. Okay. Now, what does that lead to is that the other monomer, in a sense, of aluminium chloride, AlCl3, will say, do you know what? Some of my chlorines have got spare electrons on, so it's got that lone pair of electrons on it. Okay, so what will happen is that 2 AlCl3s will bond together, but this is what I need you to focus on, is that in each case there is a dative or coordinate bond being offered by one of the chlorines on each of the, in a sense, monomer. Okay, so you need to be very careful when you're representing dative or coordinate bonds, and you need to show it as being an arrow. Okay, it is worth noting just very briefly though that aluminium chloride can exhibit its structure of AlCl3, okay, but this is only really present at very elevated temperatures. Okay, if it's present as its monomeric form of AlCl3, it is planar and it is symmetrical. I'll be focusing, touching and dipping into these VSCPR theories of molecular shapes as well, because that again is a very synoptic element that might creep into your unit 3 and 4 quite regularly. Okay, so tetrachloroaluminate, okay, so it's aluminium chloride and it can form a coordinate dative bond with a chloride ion. Now, the reason I've dragged this into what ultimately is a Unit 3 topic is I'm hoping that you are well into your organic chemistry now, and you've come across tetrachloroaluminate in its catalytic role, like the Friedel-Crafts reagents, etc. So you've come across this hopefully, and this therefore shouldn't be unfamiliar to you. So it's used as a halogen carrier catalyst. Okay, so it's used in things like chlorination of benzene. So it gives rise to electrophilic substitution of that benzene ring. Okay, so I'm hoping, I'm not going to dwell on it, but this drags again into that Unit 4 element, but ultimately aluminium chloride touches on Unit 3 chemistry, so to do with the expansion of the octet rule, etc., and the electron deficiency nature. So all of this should be familiar to you. Okay, so just to recap on something else that you hopefully came across in Unit 3, which is this donor acceptor compound. So one of the most common donor acceptor compounds you'll come across is that between ammonia, which obviously has that lone pair on the nitrogen, and the electron deficient compound of boron trifluorides, so BF3. Okay, so what happens there is you've obviously got, again, if I focus on it, you've got 6 valent electrons for that boron, so it's electron deficient. But look, you've got ammonia here, the nitrogen of which has got a spare or lone pair of electrons. What happens is that the nitrogen offers its lone pair and coordinately bonds to that boron trifluoride. Okay, and what you get is this compound, and as I mentioned earlier, okay, do not lose focus of this. You need to represent a dative or coordinate bond differently to a normal, should we say, covalent bond. Okay, so what shape does it have? Well, ultimately, you've got 4 things surrounding a central bonding atom. So that boron actually has 4 bonding pairs around it, and as a consequence, it is tetrahedral in nature. Even though it's not quite a perfect tetrahedral, it's quite distorted at times, and that's due to the hydrogen, boron, and hydrogen angle being less than 109. Okay, right. Period 2. This is the third thing I want to touch upon, is this expansion of the octet rule and why and how it comes about. Okay, so in period 2, so the period that carbon belongs to, you've got a maximum of 4 electron pairs around that central carbon atom. That's why methane is CH4, etc. That's why carbon dioxide is carbon dioxide. However, in period 3, which is the period that starts with sodium or across to argon, you've actually got a maximum covalency, which is greater than that. So it gives rise to alternative chlorides, for example. So phosphorus can quite happily exhibit 2 forms. So PCl5 has got 5 electron pairs, as opposed to what you'd initially probably expect, which is PCl3, which has that valency being what you'd expect it to be, which is that octet rule being satisfied. So you've got this potential for expanding the covalency of that atom. So as I said, phosphorus exhibits as 2 different chlorides. So you've got PCl3. Just to touch upon quickly, then, what sort of shape would you expect PCl3 to exhibit? Well, you've got phosphorus with 5 valent electrons, 3 of which are there for bonding. So you've got 3 bonding pairs. That does mean you've got a lone pair. And hoping that you can recall from Unit 1 in Year 12 that if you have this instance of 1 lone pair and 3 bonding pairs, it would exhibit the shape of trigonal pyramidal. Differently to that, then you've got PCl5, which now has a different shape entirely due to the fact that you've now got more bonding pairs around it. So it picks up a different shape, and we call the shape of that one trigonal bipyramidal. Okay, how does it come about? Well, again, it's to do with this promotion of electrons. Okay, so what is possible in this case is that, of course, in the 3rd period, you've got availability of not only an s orbital and a p orbital, but that d orbital. Now, you are aware that that d orbital in most circumstances remains empty, of course. Okay, it's vacant, but that doesn't mean that it can't be utilized for bonding by promotion of electrons amongst each other. So what happens is that you have promotion of the 3s up to that vacant 3d, and that again opens up the number of unpaired electrons. So you go from having 3 unpaired electrons to having 5 ultimately. That then gives rise to the expansion of the octet rule. Okay, so it's called hybridization. Again, something I'm hoping you're familiar with. Okay, so what shape would that be? Well, I'm hoping that you are familiar with that compound, and it actually is an octahedral compound. Okay, I'm sure I don't need to emphasize it, but octa does instinctively somehow suggest 8. It's not that it's got 8 things around it, it's still only got 6, but the 3-dimensional shape it orientates itself into obviously has 8 faces to it, hence the root of the word octahedral for you there. Okay, so don't forget, revisit that VSCPR and be familiar with the confidence of saying, all right, this is the shape if I've got this many bonding pairs, this is the shape if I've got this different number, and of course you have to remember the bond angles as well, so do not forget that. The last thing I want to touch upon the content then, if I go on and tackle a few of the past papers for you, is that boron nitride is isoelectronic and isomorphism between the 2 species. So boron nitride is isoelectronic with carbon. Now carbon, you'll remember from year 11 bonding, that first unit in year 11, has got primarily 3 main allotropic forms. And so you've got the diamond, you've got the graphite, and you've got obviously those nanotubes that you got familiar with in year 11. Well, what do the word isoelectronic and isomorphism actually mean? Well, the first one, to be clear, it has got the same electronic configuration. So because boron is in group 3 and nitrogen's in group 5, when you bond them together, it's actually therefore the same electronic structure within the entirety of the structure now as would be a single atom, so group 4. So it's to do with the fact that mathematically you've got 3 and 5, which averages out at 4, and then you've got them being isoelectronic with each other therefore. Isomorphism, it just means that it's got an identical structure. Okay, and I'll show you this diagrammatically in a minute. Okay, so they're again giant covalent structures. So how is boron nitride similar to the allotropes of carbon? Okay, well, graphite, I'm hoping you're very familiar with how graphite looks. Okay, So you've got graphite there. What I want to really emphasize here, because there are differences, of course, between boron nitride and the allotropic forms of carbon, is that graphite is not in what we call register. So a carbon in one hexagon layer doesn't directly lie above the carbon beneath it in a ring. So it's slightly off register, unlike boron nitride we'll come to. So be careful. One layer of graphite doesn't directly lie above identically the layer below it. Diamond, hoping again you're familiar with being able to identify graphite structure. And then nanotubes was something relatively new that possibly you hadn't heard of until year 11, but you're familiar with by now. Okay, so how does that link into the boron nitride? Again, you've got two main. So in graphite and diamond, you have what was the hexagonal form of carbon, and you have the cubic form. That's no different for boron nitride. Okay, so again, you've got the HBN, which is the hexagonal boron nitride. Very, very, very similar to graphite. Okay, so there are similarities, but please do not lose sight of the differences as well. Okay, so you've got hexagonal sheets formed by 3 bonds to each boron and nitrogen. The sheets are, in this case, in register. So unlike graphite, these layers directly lie above each other. Okay, you've got weak intermolecular forces, just as you have in graphite, between the layers. So they, again, slip past each other very easily. This time, however, you've got polar bonds present between the boron and nitrogen, primarily because you've got that difference in electronegativity. This time it's an insulator though, because you've got no free or delocalized electrons between those layers, so it does not conduct electricity, and that can actually make it a useful property. So you can make nanotubes by bending over the layers as a consequence of that. Okay. Use of the boron nitride was a good insulator, so it's used in electronics as a substrate. It's very soft, so again, it's a good lubricant. It's got high dielectric breakdown strength, so it's got, again, revisiting that electrical insulating property. Okay, there is a problem, however, with it, which is that it does oxidize at high temperatures. That can be a huge issue. Cubic then is diamond-like in structure, so it looks very similar to diamond. It's the second hardest material known after diamond, in fact. It's got a very high melting and boiling point due to those strong intramolecular forces. It's chemically inert, it's wear resistant, hence it's the second hardest material known, and it's got extremely high thermal conductivity. Okay, so what are we doing with the cubic form of boron nitride? Well, in the future, and it's been developed more and more as we go on, but they're being used as insulating coatings around chains of buckballs. So leading back to another allotropic form of carbon than to the buccarine one. And it's also being used as insulating conductors for nanowires, okay, which are in the region of about 2 nanometers in diameter. Okay, so very exciting future development of these materials, I'm sure. So past paper questions based on the P block then. So let's focus on these. Okay, so you've got why boron forms compounds with +3 and +1. Well, it's worth 2 marks. So let's make sure for a start that you focus on the fact that you need to be saying 2 things. So it's classically just asking you, and it will be sometimes disguised, but what it's asking you to do is explain the inert pair effect, because we know that boron is right there at the top of the group, and then you've got at the bottom you've got thallium. Okay, yes, it's possibly not what you expect, because it's not the classic group 4 that they're focusing on. We're focusing on group 3 here, but as I outlined to you, the inert pair effect is evident in group 3, 4 and 5. So what they're asking you to focus on there is that the +1 occurs due to the inert pair effects, so the inert S pair. Tick, 1 mark, happy days. But then please be clear and emphasize the fact that you are aware that the inert pair effect becomes much, much more significant as you descend a group. Okay, so as you go down the group, the inert pair effect then becomes apparent and much more significant. So that's therefore your 2 marks that you see there. Okay, right. Boron compounds are made of boron and hydrogen only. This is classic synoptic calculations now from Unit 1 of Year 12. So this was a Year 13 question, I'm not lying to you, I haven't nabbed it from a Year 12 exam paper. So boron are made from boron and hydrogen. Okay, so a sample of gaseous boron was found to contain 78.14% boron, and the sometimes they don't even give you the second percentage. You'd have to work that out. Okay, in this case they gave it to you, so it's asking you there, what is the empirical formula of boron? Okay, well, classically you need to then tackle this in the normal way. So I always tell my pupils, split it up into 2 columns for me, put boron on one side for me, put hydrogen on the other side for me. Okay, so it clearly says in that question you got 78.14% boron. So the first thing I want you to do is go 78.14 and you divide it by the AR. Don't forget you've got that data sheet which will have the periodic table in it. So from there you will be told that the AR of boron is 10.8. Happy days. Okay, hydrogen therefore is 21.86. Please, please, please do not be tempted to use just one, or don't rely on your GCSE knowledge, because that would tell you boron is 11 and hydrogen's 1. Okay, we've moved on significantly since year 10 and 11, so please use the data sheet that's relevant to A2, so you'll know that hydrogen is 1.01. That'll give you the following 2 answers. So that tells you that it's 7.235, and this one will come out with 21.644. Now, most of you will be able to see that ratio because you've developed your mathematical kind of seeing patterns. If you're not that mathematically minded, don't panic, okay? The next step would be then to divide by the smallest one. So you divide both answers by that smallest one. Most hopefully you've spotted that it's actually the ratio of 1 atom of boron is in ratio to 3 of hydrogen. Okay, so the empirical formula is therefore BH3. Okay, I'll show you the marking is exactly what they expect you to do. So you'd get 1 mark for showing your calculations and 1 then for linking the ratios to what they were actually asking you, which is the empirical formula. It then led on to tell you what is the molecular formula of this boron. Okay, so I've just gone back and revisited some information that was in the original question on a previous slide. Okay, so to save me just go back and forth, let's just be clear that the next step asks you to use another bit of the information that it told you the question here that the molar volume of a gas at 273 Kelvin and 1 atmosphere is 22.4 decimeters cubed. They might not give it to you directly in the question because you got that data sheet. So please, if it's not in the question, don't forget about this data that would then be useful to you in this question. So we know that we've got an empirical formula of BH3. That has come from part A, and that's what they often do. They scaffold it, so they'll ask you question A and that feeds into part B, etc. Okay. The mass of boron BH3 then, let's work that out. So this has a mass of 10.8, which is the empirical, sorry, the mass AR of boron, and then you've got 1.01 times 3. I'm sure I don't need to be telling you this in year 13, but please be conscious of bod mass on your calculators. So please use those brackets, otherwise things go a bit pear-shaped, shall we say, at times. So the mass of BH3 comes out to be 13.83. We will need that in a minute. Okay, so I'm going to come back to that in a minute. Don't forget to use it. Okay, so what do we do with this molar volume? Well, it tells you that the molar volume of any gas is 22.4, and it told you that 232 grams occupied 1 decimeter, okay, at that temperature. So what you then need to do is work out how many moles was produced. Okay, so the number of moles, okay, is going to be therefore 22.4, which is what you were supplied with. Okay, and then you will be, sorry, so 1 divided by that, because it occupies 1 decimeter, this amount does, and 1 mole classically would occupy 22.4. So the number of moles comes out to be 4.46 times 10 to the minus 2 moles. Okay, can I please emphasize again, I'm sure you're aware of it, that you need 3 sig figs in most mathematical answers. Okay, based on that, then if you then apply another formula you've picked up in GCSE, which is N is equal to M divided by MR, okay? Rearranging that to get to what you want, which is the MR. MR is therefore M divided by N. So if you put in the numbers that we've just got, which is 1.232, the number of moles we've just worked out, which is 4.46 times 10 to the minus 2, it gives out to you the atomic mass of 27.6. Okay, so if you look at it, we know that BH3 itself weighs 13.83. We know that the molecular mass is 27.6. Hopefully, again, you can see that pattern quite clearly. So if BH3 is, as I said, 13.83, we know that the MR is, as we've just calculated, 27.82. That is a ratio, therefore, of 2, isn't it? I'm hoping you can spot that. So that means that the molecular formula is therefore going to be twice as much. So you're going to double it up. So it's B2H6. Okay. So that is relying on empirical formula calculations from year 12. But it's synoptic in year 13, so you cannot put it to one side. Right, explain the term electron deficiency. I'm not going to dwell on this too much at all. Okay, because I'm fully aware that I'm running out of time. So electron deficiency simply tell the examiner for 1 mark that he doesn't have an octet. Okay, balancing, it seems to still be the big bad wolf for certain people. I wished it wasn't, but it wasn't, but it is. So what I'm going to focus on is the fact that you've got boron 5 times there and only 1 there. So I'd always advise that you start with the one that obviously sticks out like a sore thumb. Okay, so that tells you that you automatically need to take that up to 5. Okay, if you then focus on the fact that you've now created, okay, 3 oxygens, and I'm focusing on the oxygen because the oxygen only appears in water, so that'll allow you to balance the oxygens in the water. So 5 times 3 is 15, so you're going to have 15 waters created. And as a consequence, if you now add up how many hydrogens we have, okay, on both sides, you'll need to balance it out. That means I've got 12 hydrogens there. Okay, so it's just a case of calmly going back and forth. Now, it's a mark, and I know it sounds like, oh, if I don't do balancing, this is not my best friend. Please persevere, because 1 mark can make the world of difference. And it's a case of cooling your head down and going back and forth bit by bit. Okay, right, this touches on enthalpy, but I'm not going to dwell on this. The presentation will be available to you afterwards, so just please browse these at your leisure. Okay, there are lots of things that then focus on things like the hexagonal boron nitride. The answers are there. I would suggest that you use the recording, pause it at the appropriate point, try these questions yourself, and then move on. Okay. Right, I am going to focus on this before I move on, though, because again, it's a synoptic element. You need to focus on the fact that you can't forget your radioactivity decay patterns. So boron 10, now boron has an atomic number of 5. Okay, if it's 10 and it absorbs a neutron, then that means it only takes the top number up, because neutrons don't affect the atomic number. So we're still therefore at 5. Okay, if it gives off an alpha particle, what you're making is something that's lost 4 at the top and 2 at the bottom, because that's ultimately what an alpha particle mass is. So if you then just do a bit of maths, take 4 away from 11, it gives you 7. If it takes 2 away from 5, you got 3. Now, it doesn't ask for it in this question what the identity is, but I'm hoping that you'll be able to use your periodic table to work out that what you've actually created is lithium. So the mass number is 7, atomic number is 3. If they ask you to identify, you base it on the atomic number 3, and the periodic table will tell you that it therefore is lithium. Okay, right. I'm going to go on to quickly do the transition elements. So you've got 3.4 specifications there. Again, there are certain things that just seem to crop up more than others. So you need to be very familiar that transition elements quite readily form complexes. They're coloured, and you really cannot escape that section of the course that tells you why they're coloured. They exhibit various oxidation states, and as a consequence are really good catalytic elements in reactions. Okay, So transition elements, why are they called transition elements? Well, let's focus on the fact that they have to have a partially filled d orbital in their atom or as a stable element, stable ion. Let's focus, therefore, the fact that zinc isn't one of them. Okay, zinc has got a full d orbital as an element. Okay, so zinc actually is argon, and then you've got 3d10, 4s2. That's the zinc as an element. Now we know that its only stable oxidation state is +2. So what happens is that it loses them, leaving that d orbital still filled. So it's not got a half or partially filled d orbital either elementally or ionically. So it's not the transition element. It's a d block element, but it's not a transition element. Okay. So I'm hoping you are already happy with the fact that you build your atoms, skipping the 3D and then filling the 4s and then back and forth. But you are very happy with the fact that when they're empty, you empty the 4s before you do the 3D. Okay. Why do they exhibit oxidation states? Well, it's because the energy of the d orbitals are all very similar. So successive ionization energies don't really exhibit any large jumps as you came across in Unit 1. So, you know, there are, when you plot it, it's quite a level plot that would be seen on a graph. Oxidation states, okay, now it's unfortunate but true that you have to be able to recall which one's the most stable of the oxidation states. Okay, first thing off as well, please be aware that all the oxidation states are positive, and that's because metals form cationic species. Okay, so let's just be clear with you that scandium only really shows one anyway, so that's an easy one to remember. Okay, titanium tends to be more happy as it's +4. Vanadium is happy as it's +5. Chromium, hence its good oxidizing action, is happier as a +3, which is green in colour. I tried to get the closest colours I could in this. They might not be perfect, but they're not too bad. You've got manganese, that's 2. Happiest. Iron, you learn from GCSE, is happy as it's +3. Cobalt is happy as +2. Nickel, again, +2. Copper, +2. And then obviously zinc, but don't forget that zinc is not coloured in its compound, and it's all to do with the fact that it doesn't have any vacancy in its d orbitals. Okay, why are they good catalysts? Well, first off, let's be clear that catalysts are meant to increase the rate of reaction, and that's because they offer an alternative pathway that's lower. Okay, now most of the transition elements are heterogeneous in nature. What does heterogeneous mean? Well, hetero, as I'm sure you are aware from year 12 and built upon in year 13, hetero means that it's in a different, hetero means different. So it is a catalyst that's in a different state or phase to the reactants that it is catalyzing. Okay, for example, from GCSE triple award, you got that final unit which incorporates the Haber process. So you're familiar with iron catalyzing the gaseous system for Haber process. It's going to haunt me for the rest of my life that one year there was a question about margarine, and I had never taught outwardly that my year 13 would wear that making margarine is often hydrogenation in nature. And the question I think asked, what was the catalyst used in margarine production? All my pupils are horrified because Miss had never told them that it's classically nickel, because it's an example of hydrogenation. Okay, polymerization is another one that's catalyzed commonly by transition elements. Nitric acid is another one that's catalyzed quite commonly. Okay, so all of these use heterogeneous catalysis. Okay, so they use them in these different states to the reagents. Okay, I need to quickly move on to the transition metal complexes. So transition element ions are often quite happily surrounded by ligands. Okay, so they're made up of transition metal ions centrally, and then it gets drowned or surrounded by these ligands that then datively or coordinately bond to that central atom, central ion, okay, which is usually transition metal. So they form in this normal way that all other coordinate bonds form. I did cover that in the earlier session now. So again, if you need more in-depth, either go back to the beginning of this recording or go to the transition metal recording that I think Mr. Black was responsible for last spring 2022. Okay. So complex shapes, they're often tetrahedral or octahedral in shape. So again, links back to the VSCPR theory that you did in year 12. Okay, so octahedral is the very common one, but you do have tetrahedral ones as well. Okay, they battle each other. These ligands will often do what we call ligand exchange, where they will battle who gets the most occupation. So who gets to occupy the essential metal ion most. Okay, you do, as I said, have tetrahedral complexes as well. So the most common one you need to be familiar with is that copper, tetrachloride, etc. Okay. Right, the colours, they might not be perfect, okay? So I would say learn the literature colours because you are expected to know them, but those aren't too far off. So you got the cobalt often shows blue and pink. Then you've got the chromium that's often green or, well, violet, but it appears green because of ligand exchange. So you need to be up to speed with the shapes of these. You need to be up to speed with the colour of them, okay? Why they're coloured? Well, it's all to do with the DD splitting. I'm not going to dwell on this at all because, again, it is very well covered by Mr. Black in the D block session he did last spring. Okay, but it's to do with these D splitting up to high and low levels, and then the transition of light between them. Okay, so it's in this PowerPoint, but I'm not going to stop on them or dwell on them because you can do it yourself if you want, or as I said, Mr. Black did this really well last spring. Okay, so I'm going to go quickly to the questions. Okay, I'm not going to do too many of these because if you remember back to the advanced information, it is something you need to be familiar with, but I've done quite a bit on the P block questions earlier. Okay, so again, there is heavy emphasis on synoptic element. So this is a question I'm not going to dwell on, but it does bring in that inorganic identification that you did in year 12. So things like how do you identify the carbonates? Well, it's that fact that they would fizz. So things you would expect all carbonates to effervescence because metal carbonates give off CO2. Okay, how would you identify the rest of them? Well, you'd get precipitates that sometimes are insoluble in excess. At other times, you'll get precipitates created that on excess additions of certain reagents like NaOH will dissolve that precipitate, forming a complex. Okay, so you get things like the white precipitate because magnesium is in an S block element and they don't have coloured compounds. Iron would initially form a green precipitate, chromium a green one, lead again is a P block, so it isn't coloured in most compounds, so it's a white precipitate. But then if you add excess, okay, it says there magnesium remains as a precipitate. Lead hydroxide, the other white one, however, will dissolve, so it gives a colourless solution. Whilst the two coloured green precipitates, you differentiate by excess addition of NaOH, because iron hydroxide remains as a precipitate, so it doesn't form a complex, but chromium hydroxide will dissolve, giving a dark green solution. Okay, so that is a sense of how you'd identify the precipitates, initially by their colour as a mode of differentiation, but then excess NaOH telling you which one's which, because both would be white for Mg and Pb, and both would be green for iron 2 and for chromium. Okay, right, there's a bit there on synoptic maths again, so I'm not going to dwell on that. But again, I put the mark scheme up there for you. So if you want to attempt it, to save you looking up the question on the question bank, I've put the answers up there for you as well. Okay. Right, it says there another question. Cobalt forms a range of complex ions. Two of these are cobalt hexaaqua. So you've got 6 water molecules there. What are the structures? Well, I wouldn't stress too much. Focus on the fact that it's the 6 there, which means you're looking at a 6 pair bonding. So 6, as I said earlier, in the P block is going to be an octahedral one then. Okay, and as you clearly see, you've got 4 there, so it's going to be the same kind of shape as you'd expect from the VSEPR theory, when you've got 4 things surrounding a central atom. In this case, I know it's a central ion, but the complex shape will take the same rules as the VSEPR, so that obviously is therefore tetrahedral. Okay, so that's a simple 2-mark question. But as I said, you grab all these small marks and you run with them, because every mark makes a difference. Okay, so you can see there the octahedral shape, and you can see there the tetrahedral one. Okay, why is it coloured? Well, as I said, it's to do with the D block. Apologies, that's just telling me that I need to stop talking very soon. You've got the session that you can go revisit back from Mr. Black last spring. Okay, but it's all to do with the d orbital splitting by action of the ligand, the energy then being absorbed, promoting the electron. And then be careful here, because this is something that we do see still, okay, which is this misconception that you see the colour when any electrons fall back down. It's not as an emission spectra. The colour you see is the colour that's not absorbed when there is that promotion in the first place. Okay, so that is a distinct error that we do see. So stay away from that misconception, please, and don't make that mistake yourself. Okay, right, I'm going to skip to the last few questions. Not questions, slides, because what I want to emphasize, something I'm sure you're familiar with, your teachers in schools are really professional and they would have highlighted these things to you. But in case, let's just draw to your attention these organisers, the knowledge organisers prepared by the WJC. They're available through their websites. This is just the example of the one for the P block. Okay, in the same sense, you've got the one for the transition metals there. There's 2, in fact, for the transitional elements ones. So it's short, sharp. I'm not saying that it's comprehensive. It's not everything you need to know on topic 3, 3.3 and 3.4, but it's a pretty good summary. Okay, so please utilize them as much as you can. And the second thing is try varying your revision as much as you possibly can. So I encourage my pupils to access things like Quizlet. Okay, so Quizlet gives you a variety of resources. So they tell you to do things like flashcards, matching games, etc. So for the case of the P block, the Quizlet will quite happily tell you this is an example of a flashcard, and you click on it and it tells you the answer on the other side. Okay, so this is the matching game for the P block. So what you do is you race yourself, you basically compete against yourself, trying to sort the statements out as quickly as you can. So you'd go, I think, that was that, and you drag it to where you think it is. So Quizlet is just something really good that my pupils are accessing on a regular basis, just to give a bit of variety, really, to make it less boring. Okay, so I've put a link there on the PowerPoint when you get it that will take you directly to Quizlets that have already been prepared for you for topics 3.3 and 3.4. So hopefully it'll save you a bit of work when you get the PowerPoint from the e-sgol Carolam website. Click on it and it'll take you straight to the website, and it'll come up. That's one of the flashcards that'll come up and it'll give you the answer. That's the sorting game for the transition blocks. Okay, so variety is the spice of life. Make it less boring for yourself. So hopefully you found that useful. Hopefully, then you'll have an opportunity also to go back and look at my session from last summer. But I hope tonight at least was some light being shone on some gaps that you might have had. So good night.